welcome everyone. I'm happy to see so many people online. Today I'm going to talk about our work in IBM Research Almaden on information extraction with experts in the loop. I'm going to say a couple words about me, so where I come from. I did my PhD in Italy at the University of Bari, and I was working on named entity disambiguation, so pure text processing techniques. Then I moved to University of Sheffield in UK, and there I was working mostly on information extraction, but purely automatic information extraction. And I did lots of research on how to use semantic resources, so linked data and ontologies and so on to inform the process of information extraction. Then I moved to the University of Mannheim in Germany, and my focus shifted mostly on table interpretation, but again, mostly a purely automatic method. Since I moved to IBM Research in 2017, I started being more concerned about how do we bring on the experts. Because the thing is, like, when you work on specific projects with specific clients, you really cannot rely on what's available on the web or what's public, because many times you have to go on very specific vocabularies, very specific domain knowledge that you cannot find elsewhere. So you really need to bring the experts on board. So that's pretty much my my background. What I'm going to cover in today's talk are two main things. So the first one is which resources do we use for information extraction? How do we either gather them if they're available? How do we build them? And actually, mostly what it is how do we do both things? So we gather them from the web, and also we take advantage of human annotation to refine them and to construct new ones. So the tasks that I'm going to cover in the talk is, first of all, how to build this very simple resource, which are dictionaries, that in information extraction in NLP, they're very important. And in many domains, it's a very core task to have a solid dictionary that describes concept in the domain. So the task I'm going to cover how we build dictionary from scratch, or we advance that we grow them from what's available. And how do we refine them? How do we find items that are spurious in the dictionaries and so on? And then I'm going to show mainly one use case, which is how we use the dictionaries for distant supervision, and how in IBM, how we actually analyze data centers with these dictionaries, and I'll show that. And if I have time, it's very briefly, I'm also going to show how we use them in PDF processing tool that we've been using for analyzing pharmaceutical domain information. So with that, let's dig into the talk. So the first task that I'm going to cover is how do we build dictionaries? Why do we need to build dictionary in the first place? One would assume, for example, since pandemic, we've all started cooking from home and searching from recipes online and finding ingredients and so on. So one would expect that it is very easy to find online a bunch of ingredients, of recipes, of food dishes, dishes name and so on. They should be available online. Is that true? Yes, partially it's true. So for example, there are structured knowledge. I don't know how many of you are familiar with this, but you could go on Wikidata, you could go on Wikipedia, or the structured version of Wikipedia, which is DBpedia, and you can certainly find a list of ingredients, a list of food, a list of dishes and so on. Is this enough? I argue it's not, even in domains that are so well covered, it's never enough. So since when I moved to California, I learned that there are dishes called like sushi rito, for example, which I never heard before in my life, but it's a name, or animal style fries. In Italy, never heard of this before. But if you are, for example, an advertiser, or if you're covering the trends on the area, you really want to be up and running with the new terms, new terminology, new things. So even in the food industries that should be well covered, these are not, dictionaries cannot ever be complete. So the idea here is the following. What do we do if we want to cover, if we have something that we don't know about and we want to cover it from scratch? We want to build a resource that covers the terminology. So the idea is we take a corpus, which is the corpus that we want to analyze, and we don't have domain knowledge, we don't have too many resources, and what we want to use is simple pattern-based method and human in the loop to build the resource. So let's say we have, again, we want to build a dictionary, and we have a few items from the dictionary, and we have a corpus. What we want to do, the idea is that we take the items that we know about already, the few examples that we know, we go in the corpus and we find context pattern. We see where do this item occur. Let me go in an example because it's going to be way easier, I'm sure. So on the left-hand side, you can see my initial dictionary for food, which only contains two seeds, which is oil and onion. These are two things that I know that are food. On the right-hand side, you have a corpus made of recipes that you will contain some food item. So the corpus is cohesive, it's all about recipes. How the idea is the following: I take the items that I know being food, oil and onion, and I go in the corpus and I see where do they occur. And then I start gathering all the patterns. So in this case, for example, heat the oil is a pattern of where oil occurs. Add the onion, fry the onion. I save this. So what I do next, I go in the corpus and see where do this pattern occur again. I take this pattern and I will, and what I will find is that next to that, I will find new terms. For example, aubergine, sausage, mushroom. And you can see this was for BBC recipes because it's not eggplant, it's aubergine. So I find all these new terms. And at this point, what I do is I have these items. I don't know if they're food or not, like aubergine, eggs, chicken. What I do, I ask my expert. If the expert says, yes, these are food, I say that the new patterns that I found, like heat the oil, add the fire, fry the onion, the new patterns are good to, I say that those are actually food items. So I add them to the dictionary. Once I add, so you see now in the left-hand side, all these have been accepted by the expert. So I have also aubergine, eggs, and chicken. I use these new terms to go again in the corpus and see where do they occur. And then I collect the new patterns. And I do repeat this operation again and again and again. And every time I never show the patterns to the user. To the user, I only show the dictionary item. And if those are accepted, the underlying patterns, they get used by the algorithm. And this is is a very powerful tool because you don't want to overload the user expert with too much decision, but like a simple yes or no answer of, is this item a food or not? For a domain expert should be easy enough to answer. And here I'm using the food domain because we all are knowledgeable about it, but obviously these have been, these experiments, we do them internally on very on different sorts of domain where we really need a domain expert to decide if an item belongs to the dictionary or not. So this sounds all very simple. Does it work? Should it work? Well, our hypothesis is that, yes, it should work. And actually, the power of this is that it should work on any language because it's context pattern. You don't really know what's in the word. All you know is that you're taking left-hand side, right-hand side of an item. To prove this hypothesis, we did an experiment in different language and in different languages. So we start with a few seeds. We do this iteration and we keep extracting from the corpus until we cannot find, until the expert says there are no more items. What we used to prove that, to prove this hypothesis, we took like a parallel corpora. We did this in the medical domain. So we used data from the EMEA, which is the European Medicine Agency, that collects, this is in the European Union, so they have to have all the information translated in all the languages of the European Union. And these are all documents about medicine. So there are package inserts of drugs, and they are translated, and it's completely translated one-to-one. So the idea is that if we start from very few seeds that are drugs names, and we repeat the same experiments in different corpus, we should end up with roughly the same amount of drugs in the dictionaries in all the languages. So we did, and this is an example, right? So filgrastim is the name of a drug, and these are, the sentences that are extracted from the different corpuses and the patterns in different languages. The languages that we use from the experiments are the languages, well, first of all, that I am familiar with, but also that we had subject matter experts in the team that could, double check the results and they are familiar with the language. So we did this experiment starting with only one seed in these four languages that we selected. And we selected irbestam, which is a drug. And surprisingly enough, you can see on the graph, the 4 different colors represented different languages. We simulated the human in the loop. So we didn't have a human saying yes or no, because so what we did is we collected name of drugs from DBpedia. And we know that those are drugs. So we simulated the expert with an oracle that, whenever there is a drug name, and these are very clean corpus because they are official documents, every time there is a drug name, that's considered as correct. So we could simulate the expert. Impressively, the growth rate of the dictionary is exactly the same for all the languages, which means that it doesn't matter, and the patterns can be completely, for example, in German or in Italian or in English, the pattern can be completely different. But this doesn't really matter because, the growth of the dictionary is exactly the same. The other thing, and again, this is starting with only one seed. The other thing that we experimented is, what if we already have a dictionary? So for example, drug is a good example because you will have drug names. Of course, there will be new drug names coming, but there are some already. So if you start from a dictionary of drugs and you use that as a starting point for your dictionary expansion method, does that work? Is it still good? Does it matter which seeds you have at the beginning? And actually, no. So we used DBpedia. We took all the drugs on DBpedia. We randomly selected 20% of the drug names, and we repeated the experiment. And again, you can see, regardless of which seeds we used to start with, the growth rate is always the same in all the languages. The last thing that we observed is, okay, what is the influence of starting with only one seed, so starting from scratch versus starting from where you have already a dictionary? Well, pretty much you end up at the same place. But obviously, if you start from, from something that you have already, you save some iteration. So when we started using linked data, so the name drugs that we could extract from DBpedia, we could save about 10 iteration, but then at the end of the day, the dictionary reaches the same saturation after a number of iterations. So for example, we did this experiment, and this experiment we actually did with a medical expert. After 25 iteration, pretty much the size of the dictionaries were the same, regardless if you were starting from one seed or with a 20% of seed already. And this is in the drug domain. Just for fun, we repeated the experiment also on Twitter data. And the task here was to extract color names. So again, colors, it's something that one assumes is like, well, you can find online the list of all colors. Surely, they all processed online. Well, it's not necessarily true, and I will show some anecdotes. But the experiment that we did is we took 2 weeks of data stream from Twitter. And we, again, in the same 4 languages that we had people in the team that could, interact with the experiment and with the corpus and so on. And we repeated the experiment. So starting with colors that we could extract from DBpedia, how many more colors can we get from the Twitter corpus? And surprisingly, we could. So we could actually add, for some reason in Spanish, people talk a lot more. I don't know, they make up color names and so on. But even in English, it was surprising that we could add, in just a few iterations with the human in the loop from Twitter data, we could add 19 colors that were not covered in DBpedia. And one of these was, for example, space gray. And it was funny because that was one of the weeks when there was a new release of the iPhone, and space gray was a color, and space gray was not in DBpedia in the list of color, but it came up. And the other one was amber rose, so or azulgrana, or things like, colors that represent some soccer teams in Europe, and that were covered in Spanish and so on. These are not proper colors, but imagine if you want to cover Twitter and you want to know what color people are talking about, then you want to, cover these in your dictionary. So at this point, I'm hoping I convinced you that knowledge resources that are available online are never enough. You always want to keep your dictionary, your lexical resources up to date. And the other thing, the other aspect about available resources is that sometimes, especially if you grab them from the web, they might not be completely clean. So you can have, examples, you can have items that are actually not correct, or you can have items that are really ambiguous. An example. So if you go on DBpedia, and this actually I found out because I grabbed the list of food from DBpedia when I was doing the experiment, sometimes entities are mistyped. So the word that, if you go to DBpedia, is classed as an entity of type food. Obviously, if you're using these in a dictionary and you do some string matching, use some string matching technique, your experiment is going to pull in so much noise, because everything which is that is going to pull in, and that is very simple. I mean, this was very simple to spot because it's a stop word, but there are other things that are not so obvious to spot and will create problems in your downstream methods. The other thing, and this I will talk in the use case later, sometimes these are things that are not extremely easy to spot. But for example, Internet Explorer, which should be a software, I would expect to be classed as software, is an entity of type television show. So if you're expecting Internet Explorer in your software list, then you won't find it because DBpedia doesn't have it that way. And this, one can argue that you can use cleaner ontologies that are human curated and so on, but there will always be items that will offset your experiments. So after finding out, and this, after finding this in our experiments, we thought of the idea of how to identify. Imagine you have a dictionary. So now we are happy because our human expert helped us to build a list of food and so on. How do we inform the expert that some of the items in the dictionary might be spurious or ambiguous? Let's see how that goes. So the idea is, like, we go back to the extraction patterns as I explained before. So as I said before, we have a dictionary, we have a few items, and we use extraction patterns. So for example, I ate apple for breakfast, I ate banana for breakfast, and so on. If the corpus is all about recipes, all good. The patterns are all going to be cohesive. But if the corpus is, for example, UK WAC, so the whole coming from the whole web, you will find things like, I invest in Apple stocks. Now, is this pattern good? Well, it will probably bring in things that we don't want. So the idea here is the following. Why don't we use the underlying, and again, we never show the patterns to the user, we only show the items in the dictionary. But how can we make use of these underlying patterns to understand if an item is ambiguous or not? So this is the idea that we wanted to explore. What we do, we take whatever item we already have in the dictionary and we identify all the patterns, same as before. But now, what we're saying is, if we want to identify a score for items, and the score, this ambiguity score for each item of the dictionary, goes up if the patterns extract items that are not already in the dictionary. So for example, let me see here. So for example, if I use the pattern, I invest in stock, I will extract from the dictionary words like Apple, but also Google, Facebook, and so on. So if many of the extracted items are not already in the dictionary, then the ambiguity score for that pattern goes up. And then basically all the words will be upscored as ambiguous already. We tested this idea on two corpus. One is the UK WAC, which is a snapshot of the web. And the other one is the same Twitter corpus that we used for the previous experiment. As a gold standard, we did the following. So we went on DBpedia, and DBpedia is, for if anyone is not extremely familiar, is basically the structured version of Wikipedia, where we also have types for entities. So we have an ontology of types. So if you go on DBpedia, there are, at the time we did this experiment, there were about 400 types, concept in DBpedia. So we take all the concepts that we can find in DBpedia, so food, cars, and everything that we can find there. And we collect, with a simple query, we collect all the items that belong to this concept. Now, another very nice thing about Wikipedia is that you can find which words are ambiguous. Because if you go, for example, to Wikipedia, if a word is ambiguous, for example, Apple, there will be a disambiguation page. So all the meaning, the possible meaning of this word. And this is captured in a structured way in DBpedia as well. So you can simply do a query and see how many of these items in each concept are actually marked as ambiguous. So as a gold standard, we use this one. The list of all the concepts, so each concept that we could find on DBpedia is for us a dictionary. We treat it as a dictionary. And on the other side, which portion of each dictionary is actually tagged as ambiguous in DBpedia. Now, we ignore this. This is the gold standard. So in the experiment, what we do is we ignore the information that we have about the ambiguous term. We use the ambiguity score with the patterns that we came up with and see how many times we can actually tag the ambiguous item from DBpedia. Surprisingly, so this graph actually shows the precision at n, so n from 1 to 100. So we have a dictionary, and what we do is we rank it by ambiguity. So the top items are the most ambiguous. So for example, Apple would be very ambiguous, and so on. The precision, the ambiguity of the top one item is 95%. So we can always recognize ambiguous item. And of course it drops down, but still the first, up to the first 100, the precision is very good. And again, this is a very, very simple method because it's basically counting. There is no fancy machine learning, nothing. It's basically a count score for the patterns underneath. And the human expert, so what do we do with human expert here? So at this point, we're basically ranking. And all we want to do with this ranked list, it really depends on the downstream task. So imagine you're doing advertising. You don't really want to use, and you're going to pay for keywords, right? In the advertising, you don't really want to use a keyword which is highly, highly ambiguous. So we can provide this to the human expert and say, okay, the ambiguity score of this word, if they're choosing that word for their ad, is very high. Are you sure you want to use this one? Or if you're doing machine learning, for example, it's very useful to know that certain terms are highly ambiguous because you don't want to use that for distance supervision. And we're going to see distance supervision in a task in just 1 minute. So basically, this is just to characterize the resource. Now, as I promised, and we're halfway, so I'm talking fast, and let me know. I mean, I'm not sorry, I'm not looking at the chat, but if there are questions, Robert, you can interrupt me at any point. Let me see if I'm.
Will do. We're just joking about food names in the chat right now. No questions.
Okay, good. So, but at any point, interrupt me if things are unclear or anything like that. So as I said, so now we have dictionaries. We constructed dictionaries. And again, I kept it very simple on the food domain. But now I'm going to show how we do this for software names. How do we use this for downstream task? What we did is in IBM, we do lots of migration for data center. So what's a task? Sometimes a company comes, like a third-party company, and they want to migrate basically all their infrastructure to the cloud, or they want actually to migrate the data center physically from one location to another, and IBM is managing their data center and so on. So the task seems easy, but is extremely complicated because some of the customers are really large, for example, healthcare provider and so on. The downtime needs to be nothing. So all or if it's a bank, for example, or if it is an airline, we really cannot afford, we really need to minimize, but most time we cannot afford failures during the migration. So the data center should be up and running at all time. There are so many machines running in the data centers, and many of them, you would expect everything is very nicely cataloged and so on. But sometimes when we onboard third-party company, the situation is not particularly clear. We don't know what's running on a machine. It's extremely difficult to identify which nodes are running the database. You would expect it's simple, but it's not. And the state of the art that before starting this project, the state of the art is really like client interviews and expert interviews, and go ask Robert what's running on that machine. Did you update the machine and so on? It was very cumbersome as a task. So what we want to do is, can we use any sort of semi-automatic, because the expert can never be taken out of the picture, can we use any sort of semi-automatic methods to help this process? So what we really want to do is, given all the nodes that we have in a data center, create some sort of knowledge card that says, okay, this is what you have on this machine, and these are all the applications that are running, and all sorts of possible information that we can have about each node. What do we have? So we have graph-based data. So things that it's easy to actually grab is all the connections, which ports are open on each machine, who is talking to who in the data center. Those information it's easy to grab. The other things that we brought on board, while you have information on who's talking to who, you don't know which software is running. It's not written anywhere. So how can we take external knowledge about the software names and so on to actually cross-check this information? And how do we use the human expert to make sense of the both things together? I'm going to show two experiments that we did, and these are actually two real life data. I'm not going to say names of the clients, but one is a financial institution and a US financial institution. The other one is a Canadian healthcare organization. So again, as I said, we have knowledge about the structural knowledge, the logistic knowledge of what's running in data center and so on. What actually is not available, as I said, is what is running on a data set and which nodes, for example, are running the same application. So if I have a health record system, what are the machines that are running this health record system? We don't have that information. So the pipeline that we propose is the following. First of all, we collect all the logs and how I'm gonna tell you how text processing actually really helped in this particular case, and how the dictionaries really help in this particular case. So first of all, we collect all possible knowledge, like the nodes and the ports and so on, but also all the scripts, all the logs from the machine. So this is a huge amount of textual information that we gather. Then we construct dictionaries, and I'm going to talk about which dictionaries, and we use those to actually do some distance supervision on the logs that we can collect from the machine. Then we use the human experts, and these are people that actually are in charge of data center migration, to actually validate the information that we generate with distance supervision. With this, we train models, and we do iterations, and we refine the models again and again and again, so that we can really create a good picture of what's running on each node of the data center. And then basically at the end, we can we can construct a knowledge graph of all the data center with semantic information about each node. So first thing first, how we collect the data. We don't collect the data from the whole data center. We run collector scripts on 10-20% of the nodes of the data center. We leave it running for 2 weeks, and every 15 minutes, we take a snapshot of, again, as I said, the ports, the operating system, but most importantly, all the logs from that machine. Of all the process running, we get all the strings of the logs. And then all sorts of other, structured information. As I said, operating system, active connection, process IDs, and so on. This structured information is to construct a graph of the data center. Now, the idea, so at this point, it's like, okay, we have so much textual information, which is logs. And this is not natural language. It's still text, but it's very, very structured and very unintelligible for a human reader. So the idea here is, can we use dictionaries, and in this specific case, dictionaries of software names, like a list of software names, to actually understand what's running on the machine. And we the dictionary that we're gonna collect them from available resources on the web. Then once we use these, so the logs matched against available dictionaries of software, we use this for distance supervision. And then the human expert is going to help us refine, annotate, and validate these distantly supervised, created, annotated data to train machine learning method. Obviously, there are limitations about this method. The good thing is, like, this is a method that you can use for many tasks, not only for data center, but if you have resources available, you can do it. And then once you build a dictionary, because in the process you're going to also refine the dictionary, this dictionary is going to can be used for other tasks as well. But obviously, not all the not all the tasks have resources available. So and the quality of the dictionary might not be great, and so on. There are limitations. But in this particular case, it was very useful for us, and I'm going to show how. How do we construct a dictionary? Not from scratch, as I said at the beginning, as the method I said from the beginning, but we actually use external knowledge bases to grab a list of software. Then what we do is we build a knowledge vector space representation of all these items that we have from external knowledge. Again, we build a vector space representation of all the logs that we have, and we use simple similarity measure to actually match the two things. The dictionary we constructed from, and I'm actually copying, here I have the exact query that we used on DBpedia to collect all software names, and you can collect all sorts of other information. So for example, so in this case, we collected all software, and there were nearly 30,000, like 27,000 software on DBpedia. You can get the names, but you can get the software type and all sorts of other information. So you can collect more textual information if available. You can get the abstract, you can get the description. If you want to build a better vector space representation for each software, these knowledge resources will give you this information. So we use DBpedia, and now we have a dictionary made of nearly 30K software names. So at this point, what do is we actually match, as I said, we have a vector representation of all the strings of all the processes, and we actually do a simple match between the two, and we select every item that is above a certain threshold, and we ask the human expert to validate. Is this actually a good match? And this is it's not too difficult for an expert to say, for example, this string logs actually is Internet Explorer, and Internet Explorer is a very toy example, but there are many even homegrown software and so on that are very easy to recognize for a human expert. And once you do it, because there are so many logs about the same things, once you do this validation, it's valid for many processes in the data center. At this point, we have some initial training data built with distance supervision, but validated by the expert. And we do two things. The first one, we train string-based method just to annotate the rest of the data center. But also, we have to use, we train graph-based method. And this is because we don't have logs for all the processes. So for many, we do have string logs, and that's extremely useful for distance supervision because we can create the initial models. But then the graph-based method will help us to basically annotate all those nodes. They're still in the graph, but they have no logs attached to them. And for example, all those nodes where we don't collect information. As I said at the beginning, we only collect information on 10 to 20% of the machine. So everything else, we only have the node. We do not have string information. So the graph methods are actually, bridging that gap. As for string, we no big innovation here. We're just using state-of-the-art model and testing a few different models. As I said, the strings are just the logs, and the validation, the correct label are name of software. It could be Internet Explorer, it could be the healthcare application, it could be Oracle, it could be DB2, it could be anything like that. The model that worked the best for string-based method is CNN. And then how do we bridge the gap to the graph-based method? Actually, we simply take the whole graph, and we use a state-of-the-art graph embedding methods, so that basically we transform the graph into a vector space. And at that point, we can reuse exactly the same models that we used for the language model. So for the embedding, the normal embedding methods. I'm going to show an example here. So why actually, as I said, we don't have information about all the nodes. So in this very small picture, you can see that node 4, node 1, and node 2 actually have a string attached, which is a log that, a portion of the log that we grabbed from that machine. And with distance supervision and with string-based method, we can actually tag those as web browser. Because, for example, if you see in P1, there is this IE Explorer, and you can imagine that is going to have a very high string similarity with the tag name Internet Explorer. So that is going to be tagged as web browser. Or Chrome, for example, in P2 is also going to be tagged as a web browser because it has a high similarity, the string has a high similarity. But node like P3 and P5, we have no information. So P5, we have very limited, is server.exe. We cannot match that with anything. And that's why, by having the embedding of the graph, and because, for example, P3, P2, and P1 are all children of P4, which is a web server, then we can infer that also P3 is a web server. It's not going to be for sure, but the likelihood is very high. Experiments. So as I said, we actually use this method on the quantitative experiment has been done on two big data centers. We actually used the whole system on more than that, but the experiment is only on 2 data sets. One is the US financial, and the other one is Canadian healthcare. And we actually the US financial, we started completely from scratch, building the labels and so on. For Canadian healthcare, we actually could reuse the initial models that we trained on US financial to instead of starting from scratch with the distance supervision, we could start from the model already. As I said, the number of software entities that we could collect to DBpedia was nearly 30K, so 27,000. We have more than 1 million running processes that we collected, and this is the 10-20% that we collected from the US financial data center. And what we do with distance supervision is we select every tag that has a similarity score above 65%. And this leaves us with 600,000 tagged process, and they match only 600 different tags. So of all the 30K software names that we collected from DBpedia, only 600 were matched in this data center. After the SME validation, so after the subject matter expert went on the validation, so many of these tags were not deemed useful, because at the end of the day, yes, they're valid, but software matter expert might not be interested in certain software, and many, for example, could be game, like software games. And sometimes in data center you can find logs of people. It's weird, but you can. So many of those are not useful to understand the nature of the data center. Those are anecdotal. So many of them have been discarded, and we're left with 122 unique tags. And so what we do at each iteration, so we start with the distance supervision. The first step is distance supervision, and every step we train a model, and this is string-based model. We label the data, and then we select the top scoring results for the human expert to validate. And we keep doing again and again and again and again, because the results will improve. So we did about 10 iterations. After 10 iterations, the subject matter expert was actually happy that the information that they wanted to understand from the data center was covered. It was about 10 iterations of retraining. And the confidence score that we use, so while for distance supervision we use, because this is similarity, so we use 65%. In this case, because we already have trained model, we can basically select anything which is in the 90s as confidence score from the model. These are the results. I just want to remind you, it's like the blue one is the US financial, and this is where we start completely from scratch. So the first iteration, number one, is completely distance supervision. While for the yellow line, which is the Canadian healthcare, we start with the model trained on the US financial. The thing here is, like, you can see, so when I was talking about spurious item or missing items in lexical resources. So if you see iteration 3 and 4, and then the accuracy starts going up again afterwards in the blue line, it goes down. And that was when actually and this is how we knew that Internet Explorer, it was tagged as a television show, because there were many processes that were not tagged, and the subject matter expert was surprised, because like, this should be very easy to tag as Internet Explorer, but it wasn't. And actually we realized we didn't have the tag, and that was the reason why the model could not attach that tag. And then we found out that actually Internet Explorer was tagged as a television show, and that was the case for other. So the Internet Explorer is like an example, like a knowledgeable example that everyone would be familiar with that. But is the same case for homegrown software. So sometimes there is software which is internal to a certain company, is named a certain way, and you cannot find that on DBpedia. It's all internal, but the subject matter expert knows about it, and they can specifically add that tag. And then at the next iteration, the model will pick up that tag, and the accuracy will start going up again. Again, it's like, yes, television show. So the results, as I said at the beginning, no much innovation on the model here. We just really used state-of-the-art model with not much tuning or anything like that. And CNN is the one that performed the best, and actually string-based methods are the ones that work the best. Nonetheless, all the other methods are actually all graph-based methods. The difference, so we tested logistic regression, SVM, and CNN for all of them. And then we tested different graph embedding methods. It doesn't change too much, and the accuracy, the results are not fantastic for the graph-based method. Nonetheless, for nodes where we have no strings, this is the only thing that we have, and we cannot validate it because we're not going to ask the human expert to validate blank nodes. What is blank node? Because it's going to be tedious and laborious to do so. But still, that help us to build a graph, even if it's not completely, it might not be complete as information. It still create dots that might be useful for the subject matter expert. And I just want to show, I know I'm conscious of time. I am gonna just show the kind of, this is actually a software that is used for migration. So you can see the blue nodes here are the one where we collect the collector script was run. So we have all sorts of information about them. The yellow node or orange node are the ones that are inferred. So they were not collected from the script, but we could make information and so on. And then because we could attach all this sort of information to each node, we can actually do all sorts of semantic query, drill down on anything that is running, for example, network discovery services or pharmacy services or remote desktop and so on. And then for each, as I showed at the beginning, for each node, we can actually go inside in each node and see what's running, what are the port open and so on. So this is like, just to show it's a real use case where we basically went from a bunch of software names that we could collect from DBpedia to actually create a picture of a data center with really minimal user validation. As I said, 10 iteration of just validating the data, and then you can basically give the subject matter expert a full picture of the data center. Now, I was as I said, I was planning. I'm going to go very, very quick because I was planning. I'm going to skip the rest. I just want to give you an example. The other, like, just one information about. When you are dealing with subject matter expert, one extremely important thing is to respect the environment that they use already. So coming up with a new tool for annotating or it's very disruptive for subject matter experts. They want to do their job the way they're doing it. And we had this experience with, we have a team that curates, extracts knowledge from medical pamphlets, so package inserts from drugs. So FDA every 6 months release a new package inserts for a drug. So we have a team that internally curates the change of information between pamphlets and that maintain a database of adverse drug reaction and so on, because we serve many pharmaceutical companies. So it is very important. And again, sorry if I'm skipping slides very quickly, but I am, very conscious of time. So it is very important to respect their system. And what we did is actually we built dictionaries of drugs. We didn't build them. We used whatever was there. So we used Medra and all sorts of ontologies that we have already. And we overlaid this annotation on the PDF. So the people that we just used Adobe Acrobat and they use it to highlight pamphlets and so on, and we overlay this on the PDF, and then giving the user the possibility to change directly on the PDF was extremely useful for them. And then once you do this, you can actually interact with the expert a lot more, because you can go above just the dictionary highlighting, and you can, for example, train model to identify sentences that are talking about adverse drug reactions. So for example, in this picture, everything which is highlighted in green is talking about an adverse drug reaction, and so on. So this is just an anecdotal thing. It's like, it's very important to respect the tools that the subject matter expert are using already. And I am 5 minutes from the hour, so I really want to leave a couple of minutes for questions. And yeah, that's it.
Wow, thank you. That was incredible. I kind of feel like you covered almost every topic in natural language processing. If I was keeping count, as lexical resources, plain text, structured text and logs, database integration, leveraging metadata as annotations, vector embeddings, graph models, NLP across languages, annotation interfaces in PDFs, and every single popular machine learning architecture of the last 20 years. So
all right.
I think we should just put Anna Lisa in charge of all NLP from here on out, because I think I think we covered it all. So in the interest of time, I'm going to quickly combine and speak some of these questions in here. There are a few different questions around language models, the pros and cons of large pre-trained language models, especially as it relates to ambiguity and noise on the cons, and in the pros, the ability to generate synonyms or words with close vector distances. So curious to hear more about how those kind of recent advances might play into this work.
Right. So specifically, I'm going to talk about I'm going to answer quickly about the data center. So the reason, like, for example, like pre-trained model, they're not very useful there is because the logs have a completely different way of talking. It's very templated, like so when the language model, the pre-trained language model are not extremely useful there. And you have to do some sort of cleaning on the strings themselves, because operating system, they have slashes and things and so on. In this particular case, they're not particularly useful. For sure, when you talk about building dictionaries, yes, they are useful. And in fact, while I'm talking about simple, just a pattern-based method, we also did use, so there are a couple of works that we did actually integrating pre-trained model to do both things. So sometimes statistical patterns are extremely useful for certain language or for domain that are not covered and so on. But for other things, you can combine. So actually the software that we have you can choose the algorithm, or you can combine them, because sometimes one or the other work better. I wanted to I picked up, sorry, I couldn't follow too much the chat while I was talking. I thought I could, but I couldn't. So there was a question about who are the subject matter experts. For the data center, actually, these are the people that do the migration. So people that know about mainframe and so on. So the people that actually move the machines. And the annotation has been done by mostly one guy. Another one was helping, but then the software itself has been used by 15 practitioners. So the results of the software, while one helped us to create the tags and to train the models, the software itself was used by 15 practitioners, and these are the people that actually do the data center migration. And actually they go to the client, and it's very useful to go to the client with the software that can show, okay, this is your data center, and this is what you have in your machine, and these are the ports that you're using, and this is a connection here, and so on. Please go ahead, and I hope I answered the first question.
Yeah, I think Roger's question is a great follow-up, especially because it sounds like it's human in the loop rather than humans. How do you try to minimize the amount of psychological bias from that one person?
Actually, in this particular case, we don't, to be honest. And this is a domain where, no domain is free of bias, of course. But when you talk about software, first of all, you don't have that many experts, that many people that know about processes, and there is little bias. The thing that can happen, someone is missing some processes there. When it comes to, for example, we did in the past some experiments on the medical domain, which we're not covering that much anymore these days. We've shifted more to other stuff. But in the past, we were using actually doctor experts, like medical doctor, to do the annotation on adverse drug reaction. And there, actually, we could capture some bias. The thing here, we do personalized models. Most of the times is like internally one organization, they have guidelines and they adhere to the guideline. We don't cover too much. What do we do? How do we actually combine and make sense of when we have different opinions on things? We don't cover that. So I don't cover every topic in the world.
Okay, so all right. Not every part of quality control for annotation.
We mostly going to the truth. Like we hope there is a single truth in the domain we are covering, basically.
Right. I've seen that before, where domains are complicated. You just nominate one person to be the truth, and and you just have to appreciate that you're going for consistency over lack of bias, and
I picked something like just right now. Someone asking about PDF annotation tool.
Yeah,
no,
thanks for the question.
Is actually Adobe PDF, and you can overlay annotation on Adobe. So it's basically a layer of annotation. It's not our own. So once you put this annotation in the PDF, any Adobe, the free version of Adobe will actually show your annotation on the left-hand side.
Okay, wonderful. If anyone's got any burning questions, I have a couple more minutes. Do you want, Lisa?
Yeah, I'm.
All right. So if you have any more questions, please add them to the chat. There's a specific question further up about how you'll measure in context. Is it a fixed window, or are you looking for like phrase sentence boundaries or syntactic relation
Fixed window.
randomness?
It's fixed window and 6 words to the left, 6 words to the right. And we do brute force, we collect them all. And basically only a few will have hits. So it's very easy to basically prune the majority of the contexts that are not useful. And this was like, was very, there was an anecdote. We were doing an experiment on Twitter, and this was on adverse drug reaction. And at a certain point, there was a blue triangle, something that came up in the drug names. And that basically was Viagra. And it's very, very peculiar that you could pick icons as, because it's Twitter. And these things you want to capture them, because especially if you're monitoring social media, you want to make sure that that you are capturing every possible way every possible word people are using to refer the concept you are interested in. And
right, even in the emojis, that's really interesting.
Yes, and the other thing was, like, for example, there was an experiment with the police, and especially on social media, people will come up with code names for certain illegal substances, and those things are not in any dictionaries. But if they're talked about the same way, right? So it's like there will be a way that people refer to, okay, I'm selling drugs here, or I'm doing this here. So you could capture new code names for things.
That sounds like a fun language model task to come up with new fake code names for for drugs. Dorian, I've now asked this question twice now. How is the ambiguity score calculated?
It's very simple. It's just every time we do like counting, every time a pattern extracts words that are not in the dictionary, it gets upscored. So for example, if I bought Apple stock, or Apple, because the pattern I bought stock extracts other things, but many of them are not in the dictionary, that will go up. It's not +1, but it's a linear function of that. And if you want the exact formula, the exact algorithm, the paper is pointed in the slides, but I'm happy to send you links to the paper.
Okay, great. And we're up on time here, so thank you everyone for your questions. I'm sorry if you didn't get to yours specifically. Anna Lisa, thanks again for an incredible talk. I really did feel like we covered almost every important topic in NLP in 1 hour. So that was really impressive.
Robert, if you could, I don't know if once we close, if I can get the question, so I can try and reply to people afterwards. If you can save the chat, I don't know if I can save the chat.
That's a good question. If I can, I'll absolutely save the chat, and I'll send it to you, and you can answer those on the meetup page. That would probably
yes,
be
of
the best
course.
place
Yeah.
to do that. Yeah, actually, great suggestion. I don't know why I've never done that before. All right, and yeah, thanks everybody for coming. Next month we'll have the Masakani NLP folk presenting about how they're building language resources and new technologies for many languages for the very first time. So I am super excited about that. And Anna Lisa, thank you again.
Thank you. Bye, everyone.